comparison to reactions of alcohols, there are relatively fewer reactions of ethers that are of any importance. But it is possible to make ethers directly from alcohols by treating with concentrated acid. In this is the acid that propionate one of the alcohols. Generate water as a potential leaving group, and if we make sure that the acid we use is not one that has a nucleophile as its counterion, so not HCl or HBr, the best nucleophile that's going to be present is the other alcohol, which can then undergo an SN2 reaction to kick out water, much like we saw when we took propanol or butanol and made an alkyl bromide from it. The result of that reaction will be the protonated form of diethyl ether along with the water leaving group, which can then take that hydrogen off to regenerate the acid catalyst and give us diethyl ether. It's limited, in most cases, to making symmetrical alcohols. But it can be productively, or symmetrical ethers. It can be used productively to make an unsymmetrical ether if you start with one alcohol that's tertiary, like tertiary butanol, for example, and another alcohol that's primary or methyl, like ethanol, for example. In this case, we have much greater stability of the tertiary carbocation that's formed. Will result in an SN1 pathway and the primary alcohol being less sterically hindered will be the one that traps the intermediate carbocation that's formed. Because the primary carbocation is unstable, we won't get the competition from the primary alcohol reacting with itself. The primary alcohol will act as the donor, and the tertiary butyl carbocation will act as the acceptor. Last step, water or more ethanol. Frequently this reaction is just brought in the primary alcohol as solvent. Ethanol will remove that hydrogen. And we'll get ethyl tertiary butyl ether. And regenerate the acid catalyst, which in this case will be the protonated ethanol. So it's useful to make symmetrical ethers, and it's useful to make unsymmetrical ethers if one side is primary, the other side is secondary or tertiary, especially for tertiary examples. Typically, the reaction to produce a ether from primary alcohol like that is run at about 130 degrees C. If you run the reaction at an even higher temperature, elimination will take over because of the entropy favorable reaction for elimination. So if we were to take propanol and react it with concentrated acid, able to isolate dipropyl ether. But if we were to do the same reaction at 180 degrees C, the primary product would be the alkene by E2 elimination. As opposed to SF2 substitution. Ethers themselves are subject to reaction with acid. If we were to take the dipropyl ether that we're working with here and treat that with concentrated sulfuric acid, we can protonate it, which was the intermediate immediately preceding the formation of that ether. And this can then react with nucleophiles to displace the neutral alcohol as a leaving group. It's often a useful way, well, not really useful because ethers are generally used as inert solvents, but it is a way that you could convert an ether into the corresponding bromide through treatment with 48% aqueous HBr. The protonated ether would then be attacked by the bromide nucleophile in an SO2 reaction. Form propyl bromide and propanol. And we know that propanol can react with HBr to form additional propyl bromide by a similar mechanism, but with water as the leaving group instead of one propanol as the leaving group. So it's possible to cleave ethers in the presence of concentrated acids, but typically it's not the best way to isolate the alkyl halide product. Elimination is always a competing reaction, and at high temperature, elimination will tend to dominate. These reactions are seldom used synthetically, but there is a class of ethers that does undergo nucleophilic alkyl substitution reactions, both SN1 and SN2-like reactions, and that is the cyclic ether class known as epoxides or oxiranes or oxocyclopropanes. Oxocyclopropanes are made readily from alkenes, the reaction that we'll learn in chapter 12, using a reagent known as MCPDA. But oxocyclopropanes like that are also readily made from vicinal bromohydrates. By the Williams ether synthesis. A vicinal bromohydrate is a molecule that has an OH group and a bromine attached to adjacent carbons. Vicinal comes from the same root as vicinity, which means they're near, but not attached to the same carbon. So if we were to start, for example, with 1-bromo 2-propanol, we would expect to be able to make the epoxide by treating this with KOH. The hydroxide will deprotonate the alcohol in the equilibrium reaction to generate the corresponding alkoxide. And then the alkoxide ion is right in the right location in this anti-conformer to come in and do a backside attack on the bromide to form the 3-membered ring. You'll notice that the chiral center here, which is the S chiral center, hydroxide being the top priority, carbon attached to bromine being the second priority, and methyl being the third priority, with hydrogen being the last priority, stays intact throughout. So it's still the S stereocenter in the product. So the S isomer of 1-bromo 2-propanol would actually give the S isomer of the epoxide that I've shown here in the R stereochemistry. This is a stereospecific reaction. And the oxide is an anti arrangement so that the SO2 displacement can happen with backside attack. Or an inversion of stereochemistry. These vicinal bromohydrides are also readily available from the corresponding alkenes, and we'll also talk about that when we get to chapter 12. Even though there's a lot of ring strain in the product of this intramolecular Williamson ether synthesis, it's kinetically very favorable. Same molecule. And the 3-membered ring is the ring that's formed fastest through intramolecular Williamson ether synthesis. A little bit faster in most cases than the next most fastest, which is the 5-membered ring, which is in turn faster than the 6-membered ring, and the 4-membered ring, and then the 7- and 8-membered ring. So even though there's ring strain, the kinetic likelihood of collision is much larger because this oxygen is on the adjacent carbon and is very likely to bang into the backside of the carbon. As you increase the length of the chain between those two, you decrease the likelihood of it hitting. And if you want to actually do an experiment at home to test that theory, you should take a chef's knife and attach it to a 2-foot-long piece of rope, and then just start waving, attach one end to your wrist and one end to the knife and just start waving your hand around, and my guess is you'll get cut. If you use a 6-foot, this is the 2-foot length of rope. You've got the oxygen tethered to the bromine in such a way that it almost has to collide at some point. And so your collision theory, which tells you that the rate of reaction is related to the number of collisions, the proportion that occur with the correct orientation for reaction, and the fraction of those that have enough activation energy, you're increasing the number of collisions by putting the alkoxide ion and the LUMO of the carbon-bromine bond in close proximity so that they're very likely to collide with one another. Once you have these oxocyclopropanes, they undergo reactions that ordinary ethers do not because of the ring strain in the system. So whereas ordinary oxocyclopropanes can be productively opened by nucleophiles both under acid conditions and under basic conditions. So for example, 2-methyl-oxirane, which is what we see here, which is also known as propylene oxide. Propylene oxide gets its name from the fact that it came from the alkene called propylene, or propene, if you want to use IUPAC nomenclature. This will react with lithium aluminum hydride in diethyl ether. The diethyl ether will not react with lithium aluminum hydride. But the ring strain in the epoxide causes it to be reactive. The aluminum hydride ion will donate one of its hydrides to the carbon and kick off the alkoxide leaving group. Alkoxide leaving groups are normally not good leaving groups, but release of ring strain causes that leaving group to leave much more readily than it would if the ring strain were not present. The alkoxide is then protonated in the subsequent aqueous acid step to generate an alcohol. You'll notice that the lithium aluminum hydride attacked the epoxide at the less substituted and more sterically accessible end. The less sterically hindered end. And that's a general truth if you have an epoxide that's unsymmetrically substituted. All of the basic reagents, the anionic or basic reagents, will go by an SN2 pathway. And the SN2 pathway is most readily accomplished with the smallest amount of steric hindrance. There are a number of reagents that will successfully eliminate the alkoxide, including organometallics. So a Grignard reagent will react in the same way with an epoxide since a Grignard reagent is a basic and anionic reagent, it will react at the less substituted side rather than the more substituted side. So if I were to take ethyl magnesium bromide, for example, ethyl magnesium bromide would open here at the less substituted end. It would do it in SN2 fashion. So I would invert the stereochemistry. At the less substituted carbon. And the stereochemistry if the more substituted carbon would remain intact. The reactive center is here. And we've just formed a new carbon-carbon bond. This is similar to the two carbon homologation reaction that I showed when we were talking about organometallics, where we were able to open ethylene oxide. It works best if one of the ends is unsubstituted as opposed to having a substituent on there, but it can be used in other situations as well. So you'll notice that the chiral centers in this, and now the substituent priorities have actually changed. So it did go with inversion of stereochemistry, and the chiral center here is R. The top priority is now the carbon attached to oxygen, followed by the ring carbon, the CH2 that's attached to another carbon, followed by the CH2 that's attached to a CH3 as opposed to another CH2. So your priorities are 1, 2, 3, and hydrogen is 4. So we get R stereocenter. The stereocenter here, by contrast, did not change. Here we have number 1 priority is the oxygen, number 2 priority is the carbon that's attached to oxygen, 3rd priority is the ring, and the methyl group is actually the lowest priority. So this is the R stereocenter here, and it is still the R stereocenter in the product. Aqueous acid workup, as always, for the highly basic organometallic reagents or hydride reducing agents, transfers the proton and generates the product alcohol. But it doesn't have to be a strongly basic reagent like an organometallic or a hydride reducing agent in order to accomplish this reaction. Even relatively less basic reagents like sulfhydryl groups or alkyl thiolate groups like CH3S minus, which can be available as a potassium or the sodium salt, will undergo SN2 reactions at the less substituted end of an oxirane or epoxide to generate alcohols after protonation in a subsequent step. Cyanide ion would also react. The alkoxide is not stable, but the release of ring strain allows it to leave in this particular case where you would not normally have an alkoxide leaving. You can't react a non-cyclic ether, for example, with a basic reagent like this and expect to get the alkoxide as a leaving group. So under basic conditions, it will always open at the more sterically accessible end, and it will do it by an SN2 pathway with inversion of stereochemistry at the reactive carbon and maintenance of the stereochemistry that you had at the other end of the oxirane. Epoxides will react under acidic conditions, though. So if we were to take one methyl cyclohexene oxide and treat this with aqueous sulfuric acid, we would open this up to a diol product. And in this case, it will be a stereospecific reaction to generating a transdiol. Hydronium ion is the acid, because sulfuric acid is a strong acid and completely dissociated in water. So we'll protonate the epoxide. And you would normally think that this could leave spontaneously as a neutral leaving group, which would generate racemization, and you would get a mixture of cis and trans diol. But in fact, even though this bond partially breaks, the oxygen, since it's tethered there to the adjacent carbon, doesn't leave completely, and it stays hanging around, so that even though it's SN1-like, it's unimolecular, and we have first-order kinetics. We still get a stereospecific inversion. So the kinetics differs under basic conditions. Bimolecular kinetics, second-order observed kinetics under basic conditions with anionic nucleophiles, first-order observed kinetics under acidic conditions. Both of those reactions are stereospecific with inversion of stereochemistry. So we say it's SN1-like, as opposed to an SN1 pathway, because there is no discrete carbocation intervening. There's a larger partial positive charge here on the more substituted end than there is on the less substituted end. And that causes the water, which is the nucleophile in this case, to be more strongly attached to the tertiary position, attracted to the tertiary position, because of the greater Coulombic interaction with the larger partial positive charge. And we know that Coulomb's law says that as the partial positive charge increases, the force of attraction will increase. The water will therefore attack here from the top face, pushing the methyl group down and kicking out the leader group. So we will end up with the stereochemistry at our less hindered side remaining what it was to begin with, and an inversion of stereochemistry at the more hindered end. And we'll need one additional step to generate the neutral alcohol. And regenerate the acid catalyst. Trans-diol product. If instead of reacting with aqueous acid, we had reacted this with aqueous base, we would have expected to get a transdiol, but in this case we would have expected the alcohol at the less substituted position to be the one that points up, and the alcohol at the more substituted position to be the one that points down. So we would invert the stereochemistry at the opposite stereocenter, since hydroxide would attack SN2 at the less substituted end, in order to minimize the amount of steric hindrance. Basic reagents react at the less substituted end under acidic conditions. You protonate the epoxide, and then that's opened by the neutral nucleophile at the more substituted end because of the greater coulombic attraction to the larger partial positive charge at the tertiary position as opposed to the secondary position. Even though it's not a full positive charge and we haven't completely broken the carbon-oxygen bond in that intermediate, it still maintains a close enough relationship to the oxygen that inversion, stereospecific inversion is seen.